Here we are in chapter 7 and we haven't talked about a single chemical reaction, at least not in any great detail. We've looked at atoms and electrons and bonding and periodic trends, but we haven't put it all together yet. And some of you have probably balanced equations and have looked at equations in high school, and so part of what I'm about to teach you maybe review and it'll be a little bit easier. So we're going to be balancing reactions and looking at some reaction stoichiometry. So we're going to look at chemical reactions. So we have to distinguish between physical and chemical change. Now, physical change we've discussed. That's essentially, or most of the time, a change in phase or state, right? When you're going from one phase to another, but you're not changing the substance chemically. The example given here is water, which of course is, as we know from previous chapters, it has its two-part hydrogens and 1 part oxygen in a 2-to-1 ratio. We can draw its Lewis structure. We know it's covalently bound, and we also know that there's an intermolecular force called a hydrogen bond where the oxygen binds weakly to another hydrogen here, and we have this three-dimensional network where these water molecules are stuck together, which is the reason why it is a liquid. And then when you heat this up, you put thermal energy in. At 100 degrees Celsius, what you have is you have enough energy, enough thermal energy that overcomes the strength of this bond. And so it's a hydrogen bond, which is not a real bond, right? It's not a covalent or ionic bond. So you're just breaking this weak interaction between oxygen and hydrogen, but you're not changing the substance chemically, right? So now they can just go apart and they no longer stick to each other, so they can spread out, and that's when we have that steam here, right? So here we have these water molecules that essentially just disappear. They just dissipate through the entire room. But that's not a chemical reaction. That's a physical reaction, or a physical change, really, right? And so most of the part, their phase changes, you could consider just a simple change in temperature, a physical change. If something changes, a piece of metal is heated from room temperature to 100 degrees, it doesn't melt, but it does have a physical change. And then we have chemical change, and chemical change occurs on the molecular, on the chemical, on the molecular level here, right? Well, what's happening is the atoms are changing, right? You have the one substance turn into another. So here you have iron as a solid in a nail shown here, and it's corroding. And so what's happening is it's combining with oxygen from the air or from the water, and it's turning into a new substance. It's turning into iron 3 oxide. And so that's called a redox reaction. We can write a chemical equation for that, and we're going to look at that here in a minute. Well, might as well, right? So what we do is we're going to write iron here. That's going to be our reactant. That's going to be on the left side, and we usually like to write the phase label too. So in this case we put an S because it's solid, and then what it's doing, it's reacting with the oxygen from the air, and that is a gas. And so those are the two reactants that are combining together to form a new product. And so then we write a reaction arrow and we put the products. In this case we just have one product, Fe2O3, and that also happens to be a solid, so we put a phase label here, right? So those are the so-called phase labels. Okay? So that's just one reaction, and this is a really slow reaction, right? So remember, iron is in the center of the periodic table in the transition metal part, and it's a very slow reaction. If you leave a piece of iron out and for months, and it will not rust, but eventually it will do so, unless it's a galvanized nail. But then we have an entirely different element on the surface, and we have zinc on the surface. Okay? In contrast to iron, the group 1 metals are much more reactive. They have faster rates of reactions with water, right? So lithium, sodium, and potassium are all in group 1. They are the alkali metals. And here you see lithium is being put in water on the left. So we would write lithium, and that's a solid. And this time it's reacting with water. Okay? And so here we indicate water as a liquid, as a reactant. So those are our reactants. And what's happening here is, and as you should know, lithium has a single valence electron. It is eager, it's electropositive, it wants to get rid of it to become helium-like, so that's why it's very reactive, more reactive than iron. Iron is more inert because it has more valence electrons and it's not as eager to get rid of them, in a nutshell anyway. But so this is a very rapid, fast reaction, and so it actually gives up the electron and promotes that to hydrogen. And it then in return, so it rips that hydroxide off. Well, it splits water into half to form this lithium hydroxide, which is indicated as AQ or aqueous, right? So here we have lithium ions and hydroxide ions. You know hydroxide as a polyatomic ion from previous lectures, but those are then just dissolved. They're still there. You can't see the solid lithium anymore, but the lithium is still in the form of an ion inside of that solution. And so is the hydroxide. And the hydroxide comes, of course, from the water, right? We have this HOH. And what happens to the hydrogen here, the hydrogen is split and it gains an electron from, so it's split like this where the electrons are left on the OH to have the negative, and so you have a plus, and so that electron from the lithium actually goes to that H plus, and when two of those meet you get hydrogen gas, and those are the bubbles that you see here. That's the hydrogen gas. And again, what we have reactants. That's the stuff that reacts with each other, and then a chemical reaction takes place, and here are the products. And another observation here is a periodic trend, right? Of course, you can replace lithium with potassium and with sodium. It would have the same chemical reaction. All you have to do is replace the sodium, the lithium with a sodium or with the potassium, and they form the same products. But what you see here is another trend here. You see a more and more violent reaction as we go down within a group. So these metals become more reactive as you go down in a group. Reactivity does increase. Alright, so here's another example of a chemical reaction. This one is a little bit more complicated. It's gunpowder, which is a mixture of three solids: potassium nitrate, charcoal, and sulfur. And it's not really explosive. In order for it to have an explosive power, you need to confine it into a tight space where it can build up pressure. And so, but if you just light that on fire, and take note, we have a solid here. All three of them are solid. You get this mixture. It's called gunpowder. And look at what happens. As you light this on fire, all of the products here, most of the products here, are gases. You have carbon dioxide, carbon monoxide, you have nitrogen. These are all gases, right? And so, as you saw earlier, for the boiling water, when you go from a solid to gas, you're expanding, you're spreading the molecules apart. And it's that power of the gas generation that gives this gunpowder an explosive power, right? So you see this, you don't have to stick any oxygen in to burn it, right? If we're burning wood, we have to give it oxygen. But if we are setting gunpowder on fire, we don't need any external oxygen. We have all of the reactants, everything necessary to produce gases here, right? So these nitrates usually have that power, right? Nitrates are what's making the nitrogen and the carbon dioxide gas, right? You've got the internal oxygen here. But I'm making a very short point into a long story, right? But so we here just have reactants and products on the left and the right. They each get their phase label, and then what we haven't looked at, we will in a minute, are these are balanced, right? We have the law of conservation of mass, and so that's what we have to look at next. We're going to be balancing equations, right? So to summarize the phase labels that you might see in a chemical reaction, and they are very important, okay? It's important whether something is aqueous or solid or a gas or a liquid. It just helps you figure out what's going on in a particular reaction. But this is what you will see. It's straightforward. G, gas; L, liquid; S, solid; and aqueous is AQ, or dissolved in water, right? Which basically means, if you have, and I'm going to use the example we have sodium hydroxide. We could have it as a solid, right? You can have a sodium hydroxide, which is lye. You can have solid pellets of it, right? And so then that would be a solid. But if you put that into water, it becomes aqueous, right? And so it essentially means that you have sodium ions and hydroxide ions. But we write it together and we put the phase label there just for clarity. Okay, and this will all make more sense once we go through several of these examples. Here's a chemical reaction, right? We have methane gas. It's a combustion. A combustion is you burning a hydrocarbon. When you have something with carbon and hydrogen, or carbon, hydrogen, and oxygen, you can burn it. Our body does that. We have sugars that are carbon, hydrogen, and oxygen, and we burn it. We use it to get energy from this. This gives off a tremendous amount of energy, and we always use external oxygen for these combustions. So this is, you could really have, and we saw this, we did some combustion reactions already in one of the previous chapters where we had CX and H4, and I gave you the moles of carbon, or the grams of carbon dioxide, and the grams of water produced, and from that you could backtrack and figure out what the mole to mole ratio is of hydrogen and oxygen, and then figure out what was it? Was it CH4 or was it C6H12? And so remember that, okay. But this happens every time you have a hydrocarbon and you burn it. You have oxygen and it makes carbon dioxide and water. And so this is how we would write that chemical reaction. And here's what's happening on a molecular level here, right? So you have these carbon-hydrogen bonds that are broken, okay, and you have these oxygen-oxygen bonds that are broken. And so this oxygen oxidizes the carbon to get carbon dioxide, shown here, and water, okay. So then the water combines also with the oxygen. I'm sorry, the hydrogens combine with the water, with the oxygen to form water, right? So this is, here you can nicely see that bonds are broken and new bonds are made here, right? And that's what chemical reactions are about: bond breaking and bond making. And usually that's done, the driving force between that is to lower the energy. So these overall, the energy of the reactants is higher than the energy of the products, right? And so that's the driving force. They don't want to be in higher energy, right? Think about it, right? If you are excited, you're running around the house and you're running laps, and you don't want that. You want to really, you have to force yourself to do that. You want to sit down and relax and watch some TV, maybe do some texting or scroll on your cell phone. I don't know, play a video game. And so that's the molecules too. They just want to be on a lower level. So that explains, right? And see, energy can neither be created nor destroyed, right? So we have, when this happens, we have this energy that's given off, and that's why these hydrocarbons are great. Of course, they come from crude oil, and this is what we use for heating in the house. And so there's tremendous energy stored in the bonds. But when these bonds are broken and we make new ones, that energy is released and transferred to another form. But we have another problem here, right? We don't have a balanced reaction. We have to follow the conservation of mass. And so if we count the atoms on the left side and the atoms on the right side, what we find here, right? So you should be able to do that based on what you've learned already. We have 1 carbon here and 4 hydrogens and 2 oxygens. And on the right, we have 1 carbon, we have 2 and 1, which is 3 oxygens, and we have 2 hydrogens. So we have an uneven number of atoms on the left and the right, and so our job is to balance this equation. And the only thing we can do is we can use more of the reactants or more of the products. And so what we do here is we can say, okay, so I have 2 here on the product side, 2 hydrogens, and 4 on the left. So I need to double this somehow, right? And so the only thing I can do here is I can multiply the whole molecule by 2. And then I got to be careful. So you need to be following some sort of rules here, right? So now you have multiplied the oxygen, but you've also multiplied the hydrogen here, right? Well, the hydrogen is what we want, but you've also multiplied the oxygen. So we now have 4 and so we now have 4 oxygens here, right? So we changed that 3 into 4 oxygens, and then you need to make sure that that's correct on this side, and then you see that, oh, okay, but I only have 2 here, and so you put a number in front of it. Now we're going to come back to reactions like that and practice them, but that's essentially what we're going to be doing. We are going to be messing around with the numbers in front of and these are all right now. Oh no, this is already balanced. But usually when you write, there is no number that implies a 1, and you don't write that, right? It's understood that you need at least 1 carbon disulfide for this reaction. Okay, so here we have not much, just review. This is already balanced, and so you can double check that. We have 1 carbon here and 1 carbon here. Here we have 3 times 2 oxygens, so that's 6. And here we have 2 oxygens, but we also have 2 times 2 oxygens from, right, so we have 2 from this oxygens, and we have 4 from this, which gives me 6, so that's balanced. And so then we have 2 sulfurs here and 2 sulfurs there. All right, so let's go back up and do a couple of these slowly. And if you want, you know what, and at the end of the lecture, throughout this lecture, I have just balancing equations, and so if you want to practice that on your own, or if you've got some experience, my homework has a lot, you know, go ahead and practice that, and then come back and watch this, or or skip it, I guess. All right. So here we have 2 hydrogens and 2 hydrogens, so everything's good, but we have 2 oxygens and only 1, so all we need to do is put 2 over here, and that is now balanced. Okay? Oh well, I guess I show what's happening here, so I'm going to skip the slide and move on to the next one. This is exactly what I just did already on paper. Now let's do this one here, right? So we have, and you start with 1, and you look, and you go piece by piece, right? So you have 2 here, but 1 here. So you put a 2 in front of that nitrogen, right? So that's the first thing you do, is right. Okay. And then you see what else you've changed, right? You fixed nitrogen, but you've also made now 6 hydrogens. Okay. So you come back over to the left and you find, well, that's easy to fix. I just need to put a 3 in front of it. And that makes, and that balances the equation. All right. Let's practice 3 fairly easy reactions and then take a break. Here we have sodium and chlorine forming sodium chloride, and we have our phase labels. Here's a solid reacting with a gas to form a solid. And so I start with the left. We have 1 sodium. I go to the right, to the product side. I have 1 sodium. That's good. And I'm looking at chlorine, 1 and 2 over here. So I need to have 2. I'll multiply that by 2, which also multiplies sodium by 2, and all I need to do is put a little 2 in front of here. So that one is easy. The next one is a little bit more involved, but still not very hard, right? Iron is easy to fix. We have 2, so I just put a little 2 in front of iron. For oxygen, we have 3, but we have 2 over here, so in a way I need like 3/2 of that, right? I can take this 3 and I can put it over here, but I put that little subscript under it, right? So that tells me I need 3/2, but I can't have 3/2, but this helps me balance the reaction, because what I can do in order to get rid of that 3/2, I can multiply it by 2. And so what I want to do is I want to multiply the entire equation or reaction by 2. So 2 times 2 is 4, so I have 4 iron. And I'm going to leave the phase label out. Then that 2 goes away, and I have a 3 O2s. And so that 2 only goes away for this multiplication. I still have to apply it here. So I have 2 times Fe2O3, and that is balanced. And so the same applies here to this reaction. We have aluminum. That's a 1. We have 3 and 2. So again, I need 3/2. And if I multiply through by 2, I have 2 aluminum. And then 3 bromine. And 2 AlBr3, and I have the phase labels left out. They're not important for balancing equations. All right, when we come back, we're going to practice a few more.